explorers, and welcome to another video. Today it's Advent of Code. It's that time of year again, and I really want to see your solutions, so leave those in the comment section down below. If you want to support the channel, there is a link in the description to different affiliates where you can get great deals on things, and there's also a donation link if you want to donate a coffee to me in order to improve the quality of the channel. Day 15, Warehouse Woes. You appear back inside your own mini-submarine. Each historian drives their own mini-submarine in a different direction. Maybe the chief has its own submarine down here somewhere as well. You look up and see a vast school of lanternfish swimming past you. In closer inspection, they seem quite anxious. So you drive your mini-submarines over to see if you can help. Because lanternfish population grow rapidly, they need a lot of food. And that food needs to be stored somewhere. That's why these lanternfish are built elaborate warehouses, complexes operated by robots. These lanternfish seem so anxious because they have lost control of the robot that operates as one of the most important warehouses. It's currently running amok, pushing around boxes in the warehouse with no regard for lanternfish logistics or lanternfish inventory management strategies. Right now, one of the lanternfish are brave enough to swim up to an unpredictable robot, so they could shut it off. However, if you could anticipate the robot's movements, maybe they could find a safe option. The lanternfish already have a map of the warehouse, a list of movements the robots will attempt to make, your puzzle input. The problem is that the movements will sometimes fail as the boxes are shifted around, making the actual movements of the robot difficult to predict. As the robot with the @ sign attempts to move, if there is a box, which is an O, in the way, the robot will attempt to push these boxes. However, if these actions would cause the robot or box to move into a wall, nothing moves. Instead, including the robot, the initial position of these shown on a map at the top of the document the lanternfish gave you. The rest of the document describes the move up, down, left, right that the robot will attempt to make in that order. The moves form a single giant sequence. They are broken into multiple lines just to make copy and pasting easier. New lines within the move sequence should be ignored. Here is a smaller example to get started, where the robot will attempt to move given this sequence. Push around the boxes as follows. So first it will move to the left. Then it will move up, then move up, then move right, push a box, move right, push a box, move right, can't push a box, move down, yeah. So it's pretty much, can you push a box or not? The larger movement example has many more moves. After the robot has finished the moves, the warehouse looks like this. The lanternfish uses their custom goods positioning system, GPS, for short, to track the locations of the boxes. The GPS coordinates of a box is equal to 100 times its distance from the top edge of the map, plus its distance from the left edge of the map. This process does not stop at a wall, measured at the edges of the map. So the box below has the distance of 1 from the edge of the map and 4 from the left edge of the map. Let's see here. So the box shown below has the distance 1, 4. Yes, okay. The left edge of the map, resulting in the GPS coordinates of 1, 4. The lanternfish would like to know the sum of all boxes' GPS coordinates after the robot finished moving. In the larger example, the sum of all GPS coordinates is 10,092. The smaller example, 2028. Predict the motion of the robot boxes in the warehouse after the robot finished moving. What is the sum of all boxes? It's gonna be a little bit of a challenge here, I think. So first, I want to create a bunch of different classes. So I want to have a Java class called wall. And it doesn't really need to have anything. It just needs to have a function called public boolean movable can I move return false. And then we want to have a new Java class of box, and this extends wall. And we also should have public void move function, which does nothing because we are not movable. Generate override methods, both. And this is movable, true. And I think the move should be with a direction. Like that. And this box should have an public int x, public int y, generate constructor x and y, like that. No, we don't need that. We need to have a direction and an int map. And here we probably need an x and a y as well. These around a bit. I'm not really sure how to keep track of this, but I'm trying. There we go. And I also think this wall should have a public public static final int of north, south, west, east, like that. And we also should have a class robot, and it should extend box. That's a start. So for each string, I write that every time. Lines, and for each string character, in line split, like that. If line is blank, then continue. And for the map, we have lines. We don't know the size of the map yet. Map height equals to I, and then we will after that break, and then we can just take height, and width is the first line. Int width equals to the first line length. So then we will create an int map equals to new int width times height. So there we go. So switch character, and if case of that, then the y++ and x++. If case is wall, then map y times width plus x equal to new wall. Well, that was a morning. It's after lunch now, so let's continue and see what we can do there. So this should be a wall, and I realized that this map up here is a wall map, actually. So that's the case with that. And then we have the case of dots. And then we don't do anything. Or maybe we just skip that one. We have the case of the O, which should be box. And then we have the case of the @ sign, and that should be the robot. Right? And I also think that we need to have one more reference to the robot here. Robots are, so we can actually call on the robots. So let's just put it in somewhere and then reference it outside. So that's the big part up here. And that goes through the whole map. And I believe those were the only characters we could have here, yes. So dots we just skip. And then, of course, we also need to have X inside here because we want to reset it for each loop, like that. And then if you have the case of that, then we are moving right or east. So then we need to take the robot and move that using the map. And we also need to know the robot's X and Y. Robot Y. So here we can, the robot X equals to X, robot Y equals to Y. Then we can take X, Y, width, I guess. What do we have more? And the direction. So here we would take wall east. So let's switch this up to be a wall map. And we also want to have an int width. Do we need a width? No, we don't need a width. Because we have walls. So that should be fine. Let's skip the width. So then we're trying to move east. In that case, using the robot. Robot X and robot Y. And if this is true, we could move then the robot X plus plus. So the move operation should also have a Boolean return value. Return false. Boolean wall. Can you stop wall? Here we go. Return false. So maybe we don't need movable. Maybe we can skip that? I think so. We can actually skip movable. So that's what we're trying to do there. And then we try to move in the other direction. We will have minus minus. We will try to move up. And then we will take y minus minus, and we will try to move down. Just a b, and then we will take y plus plus. So now we have all of those. We were trying to move west here, north, south. So there we go. So the robot is trying to move, and the robot is also a box and a box. So if map, we need to handle the different directions. So switch case here. Of direction, case east, we do something. west, north, south. So there we go. If map, we need the width. Oh, of course. We always need the width. Why am I always trying to skip on the width? I don't know. I just don't want. I don't want to. So let's put in the width here. But you always need the width when you calculate things. So map y times width plus x. If that is equals to null, then we will do something else. We will do something else. Else we will take, let's see, we want to move east, so we want to do +1 here. So if that's true, else we'll try to move map x + 1 y with direction. And if that is true, far direction, but 5 found, okay. Didn't we change wall? No, we didn't. And with, there we go. So now we can move there as well. Box, that's allowed. And if that is true, then we will put this into that. And the current position that we're in is equal to null. And up here we can do the same and return true. Here we can return true as well, if that is true. Otherwise, we will return false. Let's do the same for west, but we change all of these to minus. Like that. And do a north. And here we need to do a minus in the y direction. And then south, we do the same, but use a plus sign instead. There we go. Let's see what happens. So that seems to work for that, as long as we haven't done anything really bad. We should have a good map after this. So for all lines here, and so down here we should be able to do a system out and see how this map looks. So it ended up here. I wonder if we want to print the map. That would be nice, right? So for y equals 0. Pi. Let's go for pi. Height. Pi plus plus. Like that. And then we will go do pi x, px, like that. With a width. And then we will have our print line here, and then we will have a print of a particular character, and we'll take the map. I can write it out. Map equals to pi y times width plus pi x. And if this is an instance of wall, then we will print out that. And then we will have else. If it's an instance of a robot, we will print out the robot. Else, if it's an instance of a box, we will print out the box symbol. And else, we will print out the dots. So let's see what we get printed out here. Everything is an instance of a wall, of course. This needs to be the last one. Robot as higher precedence, and then box, and so on. So let's do like this. Now it looks more reasonable. Let's see here. I think I have an open document, so I could copy over this thing we have here, over there, and we can check it out. Top row is okay. It's spot on. Cool. So I actually did it. So now we need to figure out how to calculate this. We can keep that. So let's see here. The calculation, what was that? So we want to do the GPS coordinates of a box. Sum of all boxes. So the top times 100. So if this is a box, and in this case we actually need to do, if this is a box and not a robot, let's see, cannot be applied to, of course we need a parenthesis, and not a robot, then we want to do something. So let's take an count here. Let's go for long. And count plus equals to py times 100 plus px. Right? We'll get 1092. 1092. So we have figured out the right way to do this. Let's change this up to the real case, and we get that big value. So let's try that out and see if we have the right solution for the first section. Yes, you get a gold star. I get a gold star. Everybody gets a gold star. So let's look at part 2. The lantern's fish use your information to find a safe moment to swim and turn off the malfunctioning robot. Just as they start preparing for a festival in your honor, reports start coming in that the second warehouse robot is also malfunctioning. This warehouse robot's layout is surprisingly similar to the one you just helped. There's one key difference, except the robot is twice as wide. The robot list of moment doesn't change. So get a wider warehouse map. Start with your original map, each tile, and then following the changes. If the tile contains Okay? This produces a new warehouse map which is twice as wide as the boxes are presented by that. The robot does not change size, except the robot is twice as wide. The robot list of movement doesn't change. To get a wider warehouse map, start with the original map for each tile and make the following changes. This will produce a warehouse map which is twice as wide with wide boxes that is represented by, and the robot does not change size. No, the robot is twice as wide. The robot does not change size. Make up your mind. The larger example is now look like this. Because of the boxes are now twice as wide, the robot is still the same size and speed. The boxes can be aligned such that they are directly pushed to other boxes at once. So it's just that the boxes are in two places at once. So we're gonna do the same, but in the map we need to have multiple places for this robot to be. So the robot will always be on the left hand side. The map will be twice as wide. Okay. I think we can figure this one out, but we need to make a day B, of course, like that. True. Now we take the width times 2, so we have a wider area, and then we will do width times 2 here. Like that. Or should we just say that the width should be times 2? That. So now it's double wide. We don't have to think about that. So now the X position that we have here should be increased by 2 to make it easy for ourselves. And then here, in that case, we say that we have wall there. We say that we have box there. And we say that we have the same box as well. So box equals to box, like that, and then we put that into here, like that. And we can even give the box an ID. Should we do that? Give the box a box ID, so it will be so it will be unique ID plus plus. So now we don't have that problem anymore. We could have Wilson hash code. Let's create those on the ID. So now we know that we might as well skip this one and have a real ID in the other case as well. Even if we don't use it, we might as well. I'm not sure if it's required, but one related problem, yeah. And the robot needs to have an ID as well. So we have two related problems then. And the robot here should be -1. And one related problem. The robot here should be -1. Ta-da! No related problems. So, and here when we create a robot, it should only be in the left hand side. Yes. So now we have looked at this. Then we have move wide here instead. Let's create that in box. And if we want to move in the see here, east and west direction, then that's fine. It will just work. It's north and south that is a little bit more complicated. So in the case of north, we need to check two variables. No, actually, public move wide. Could be different. Then we could have this full box thingy in the robot for its movement, and then it sends a move wide instead. Okay, so the wall needs to have a move wide as well. Yeah. Of course. So now we can move wide. Now we have a different for the wall and for the box. So now we need to figure out if the box we are currently in, because we are a box, we need to figure out if our part is on the left side or the right side. Then that side could move in a normal direction. So I think we need to move wide. Should have a parent or extra. So let's do that, and then in the wall, and that in the robot we add extra. In this case we say false, because that's the value here. False, false, false. Don't do anything extra there. Boolean extra. There we go. Here, move wide. False. False, false, and false. So there we go. So now, in the box, if we want to extra, if that's not true, then we need to check that value. If that value equals us, then we will run on this value, move wide, and then all the x, y with their true. And we can do the same for this, plus. That's what we do extra. We move that as well. And here we will move wide, false. Wide, false, and move wide, false. Of course, we need to check for null as well. Very reasonable. That was the south. We do the same for the north. I don't get why they need to change the indentation. Now we got a different map here. Let's go over and check the map they draw over here. The map is like this. Got in our example. Got this one over here. This one, I don't know why it's there. This one should be pretty much impossible. These ones are okay. The robot is not in the right direction, not right place, and so on. So no, we can't check a box. We need to check a box in the same row as ourselves. Else it will not work. Whereas we will move something completely different. It's still not possible to get this map because we have split some boxes here, which is not good. So let's see here. We should end up here at some point. Let's see what happens. I think we need to fix a draw map function, right? This we will extract to extract method draw map like that, and then we just do that after each of these. Let's see if we can figure out what's going wrong here. We want to print the box if equals plus 1, then we print that, else -1, then we print that, else we print the O. So here we see that a couple of boxes have been split for some reason. Here we want to move them, and what happens is that these two are split. These two over here are by themselves, and then we get 2 extra above, which is not at all what we want. Here we have it. We of course want to move these extra blocks. There we go. Let's try it again. Now we are thinking with portals. So if we just run this instead, what do we get? We are still splitting things up. Are we doing a better job, or is it still really bad? It's still really bad. If this is not true, then return false. But we pretty much need to check if both of them can move. And I'm back. Let's continue. So now I think we just implement that function. We implement the function, can I move north and south? If not, then don't. As this robot will check the will have the extra function in it. So we will have this function in the robot. So if those two is true, then we will check if movable if we are movable in those directions, and then we will have the wall, which is of course not movable in those directions. Movable. Is that better? Movable. Like that. And in the box, you of course need to implement movable. Generate, override methods, movable. And it's only interesting for north and south. Yes. And we will check our own position as well, like that. And the same goes for plus version. Can I move in that direction? If not, return false. So that's the extra in the north direction. And then we do the same for the south direction. No. So this robot only needs to check if it's north, we need to check if we are movable in the north direction, else return false, because this is a robot, so it doesn't care about anything else. And we should have -1 as well here. So that's the robot. And for south, we should check if we are movable in the plus direction instead. Like that. And if it's wall, we just return false. And if it's a box, we need to figure out, need to use the functionality we have up in extra. figure out which one we should check. Boolean check one, check two, and here we will return check one and check two. So if we are a box, and if we have figured out that we have a box on our left hand side, then we need to then check one is equal to movable, and it's north, so it's -1 here. And then y -1 here. So that's check one. And check two is just ourselves. Like that. If we on the other hand figure out that it's the other way around, we need to check +1 and +1. So that's the north direction, and the south direction is very similar. The only difference is that we want to check +1, +1, +1, +1. +1, +1, +1, and +1. And if any of those are false, we will not move. So what happens then? We will get an error. To check our nulls as well, because null is fine. Not having an object there, then we can always move. But if there is an object, we need to check. Of course. If that is equal to null, or, and the same goes for this, equal to null, or, this equal to null, or, this equal to null, or. Now I've done north, let's do south. So null is just empty space, so that's fine. Then the check is always true. If not, we need to check the position, of course. So when you're working with null, you need to do null checks. As long as you do that, everything is fine. And if you have any problems, you will find them if you have null pointers. So null is very useful. So let's see here. the last map, and it looks very, very good. It looks exactly, I would say, like the real map. And we got that result. And 18 is not the correct coordinates, because we are counting the coordinates in the double box size, which is not the correct coordinates. So now we need to shrink it down again. Oh yes. Everything is double. I wonder if we just can take the y coordinates and or the x coordinates change, but we only want to check those boxes where where that is not true, and this box is equal to this box, and we don't want to divide by 2. Wait, was it what? Yeah, of course, both of them cannot be null. Yeah, we don't need to go all the way out. 1921. And the right answer was 1921. So, maybe we have produced something that could give us the right answer. Let's see. I'm not sure if I need to draw all of them. Maybe we should just not do that. Draw map. And then just add here return. Like that. No, it's unreachable. It's the whole point. Why do you need to be like that? So we get that value. Let's put it in and see what we get. Yes! You get a gold star! I get a gold star! Everybody gets a gold star! Nice! We solved day 15. So, what did we do? Let's go back here and check. We, first off, created a bunch of objects. So we have a wall object, which is pretty much saying everything stops here, we can't go any further. We have a box object that we can move around, and we have a robot that moves things around. And these are themselves different objects. And in the wall object, we have the 4 directions that we need to figure out. We have a move function, we have a move wide when we are moving the wide boxes, and we also have a function that checks, is this movable? And in all cases where we're trying to do things, these are false for a wall. It will never move. Then we come to the box, and this has a bunch of interesting things in it. First off, we have this movable function. It was the last thing we wrote. And if we should move something, we need to move it in the wide. It's a wide movable one. So we need to check 2 different values and see, can we move north for both these box values? And then we check if the north value is either not null, and if it's not null and it equals ourselves, so the left hand side we have a box that is ourself, then we know that the white box is this and the left hand side. Then we need to check if we can, first off, if the position above us is either both of those are null, then we have empty space, so we can move into that. But if any of them are not null, we need to check that position and if that is movable. So can we move the thing that is north of us? And then we do the same for if we have the right hand side of us being a box, then we need to check null and if it's movable. And then we do the same for the south. So it's a lot of code just to check, can we move around? Then I had this equals an hash code, so I can actually check, is this the same object? And I have an ID for each box. And up here we have the move function. So we have the very simple move function where we just check if this a box above us is null, then we will set that box to this box, and then we set this position to null because we are not having anything here at the moment. And if that's not true, then we try to move that box above us first before we move in there. And if it's not true, of course, we will return false because we can't move in that direction. So we do this for east, west, north, and south for the move function. But move wide is a little bit more complicated, of course. So when we are moving wide, east and west are the same because we just push things around in those directions. But when they are wide, we also we need to take the extra part of this block into account. So we figure out if either left-hand side is something that we want to move or the right-hand side. And if that is the case, then we will add this extra parameter, say that this is an extra box we are moving, so we don't want you to try to move again in the other direction. So if it's an extra box, and if we find that the left-hand side or the right-hand side is the same as this box, then we will move that place as well. And then we have the same movement function that we had before. In the robot case, it needs to figure out if things are movable. So east and west, we can just move wide, as we did before. But when it comes to north and south, we first run a function to check, do we have a block above us? If not, then we move in there, of course. But if we have a block, then we need to check if that block is movable. And if it's not, we will return false. Otherwise, we will try to move it. And the same goes for south. We check if the block below us is movable. And in the case we can do that, then we do a move wide. And we extend the movable move function to the robot, so we don't have any problem to just move. And last but not least, we go through the actual function that runs this. We have a function that will draw the map, so we see that something is on the map. And if we have something on our right hand side that is the same object as ourselves, we will draw the left hand side of the box. If we have something on the left hand side, we will draw the right hand side. And if we have been able to split the box up for some reason, we'll type out an O, so we see that something is wrong. So this draw function was really good to debug this, actually. Then we have this count function. It's a little bit more complicated. We need to check that we have a box here and on the right hand side. We only count that if it's the same box and it needs to be a box. It can't be a robot, and then we will count it. So it's a little bit more complicated, this count function. When it comes to the movement up here, it's pretty simple. We have first the thing that we created, a map. So we will create a wall in two places now, because we have a wide wall. We will create a box with an ID and put that in two places because it's wide. And the robot we just place on the left-hand side in the wide spectrum. So that's the difference we do here. The robot has -1 as its ID, and we have an increment in ID for the rest. And when it comes to the movement, it's just move east, move west, move north, move south in the different directions. And we change the robot X value for each of these changes. So this was today's Advent of Code, day 15. I hope that you found this interesting. I hope that you liked this video. If you want, please leave your comments in the comment section down below with your own solutions. I love to look at everyone's way of solving things. I learn a lot by reading those, and for the rest of community, of course. If you haven't subscribed yet, please do that, and I really hope to see you in the next video.